Hello everyone. In this lecture, I shall discuss the integrating factor to solve the first order and first degree ordinary differential equations. If we recall our previous lecture, the standard form of a differential equation mxy dx plus nxy dy is equal to 0 is said to be exact if it satisfies the condition del m by del y is equal to del n by del x. Okay. If this condition is satisfied, then one is exact. Otherwise, it is not exact. Okay. Otherwise, it is not exact. Once it is not exact, there may exist one factor, right? That factor may be a function of x, may be a function of y, or both. Okay. If we multiply this factor to both sides of 1, then 1 can be converted to an exact differential equation. Okay. Now such a factor is called the integrating factor. So what is an integrating factor? A factor, coming to the definition, a factor whose multiplication brings a non-exact differential equation into exact one, right, is called the integrating factor, right? Now the question is whether the integrating factor is unique. The answer is may or may not be. Okay. Therefore, integrating factor may not be unique. A differential equation may have more than one integrating factor. So, coming to different examples and many results on differential equation, let me to introduce myself. Now, coming to my introduction, myself, Professor Susanta Kumar Paikray, currently working as a professor in the Department of Mathematics, Veer Surendra University of Technology, Burla, Odisha, India. Okay, now coming to the examples, as I have told that integrating factor may not be unique. In fact, any constant multiple of a non-zero constant multiple of an integrating factor is an integrating factor. So, a differential equation may have infinitely many integrating factor. Okay, this constant multiple is one aspect. Apart from that, we can have the different nature of the integrating factor. So let me to tell you some examples. Suppose I have a differential equation x dy plus y dx is equal to 0, right? And it is an exact one because d of xy is equal to 0, right? It is exact. It is exact. Okay. Or if I see this is my m and this is my n. So n. So this m with respect to this. So del m by del x is 1 and del n by del y is here 1 because it is written of the form x del y dx plus y x dy plus y dx. So I write it like this. Now if we think of this this del m by del y, so basically if I write it y dx plus x dy is equal to 0. Now this is m, now this is n. Okay, now what will happen to my del m by del y? Now it is del m by del y. Okay, del m by del y is here 1. And what happens to my del n by del x? Del n by del x is my del n by del x. Okay. So depending upon the standard form of the differential equations or the variable we choose, we write the conditions. Okay. So this condition is for this form of this differential equation. Now you see, suppose we have another example, x dy minus y dx is equal to 0. You see, it is not exact. Okay, it is not exact. So here this is my m and here this is my n. Okay, now you see this differential equation is not exact, or I can rewrite it minus y dx plus x dy is equal to 0. So what is my m? My m is this and my n is this. Okay, so del m by del y is equal to my minus 1, but del n by del x is equal to my 1. So this is not equal to this. Okay, del m by del y is not equal to my del n by del x, right? Is not equal to my del n by del x. So not exact, okay, not exact. Now once it is not exact, by inspection we can see, if I multiply 1 by x square to both sides of this, 1 by x square is x dy minus y dx, okay, is equal to 1 by x square into 0. So now this 1 by x square here is an integrating factor. We see whether it is an integrating factor or not, because we will write it x dy minus y dx divided by x square is equal to 0. Now this left member here is a complete differential. It is here d of y by x is equal to 0, is not it? So now this becomes exact. Now this becomes converted to exact. This was earlier not exact, but it converted to exact. It is because of what? It is because of this factor, okay? It is because of this factor, right? It is because of this factor. So this factor is my integrating factor, okay? This factor is my integrating factor, or in short I write IF, right? So integrating factor brings the non-exact equation into exact. In fact, if I multiply 1 by y square, so now let it be my equation number 1, right? If I multiply, instead of this 1 by x square, if I multiply 1 by y square, alternatively if I multiply 1 by y square into x dy minus y dx is equal to 1 by x square into 0, then what will happen? So this implies it is my minus of y dx minus of x dy by y square is equal to 0. Is it not my d of minus of x by y? D of minus of x by y, minus of x by y is equal to 0. Now it is a complete differential, is not it? Which is a, or if I multiply minus sign to both sides, d of x by y is equal to 0, okay? D of x by y is equal to 0. So I can say here, now it converted to exact, okay? Now it reduced to, which is a complete differential, okay? So exact, right? So this non-exact equation. So what is the integrating factor here? The integrating factor is 1 by y square, or I can say integrating factor is minus 1 by y square, right? So you see, is it unique? We get two integrating factors. This is one integrating factor, and again this is another integrating factor. Again the constant multiple of this is also another integrating factor. Apart from that, if I multiply 1 by xy to both sides, okay, if I multiply 1 by xy to both sides, then what I will get? 1 by xy y dx minus x dy is equal to 1 by xy into 0. Now what will happen? It is here x dy minus y dx. So if I divide it, okay, so this will be my dy by y minus dx by x is equal to 0. So is it not my d of ln y minus ln x is equal to 0? Is it not exact? It is not exact one. So it is now converted to exact. Okay. So therefore this 1 by xy is a integrating factor here. So 1 by xy is another integrating factor. Okay. So how many integrating factors? Therefore we are getting 1 by x square, 1 by y square, minus 1 by y square, 1 by xy, etc. are the integrating factor. Are the integrating factor of 1. If I say 2 by x square, if I say minus 1 by x square, so on. If I say 5 by y square, if I say 7 by xy, anything, any multiple of this, are they not the integrating factor? Also the integrating factor. So you see the remark, okay, the integrating factor may not be unique is clear now, and any multiple of this. So in fact there are infinitely many integrating factor. Okay, now let us see the methodologies to get the integrating factor. So methods to find integrating factor. So method 1 is by inspection. Okay, I am explaining here some standard examples where you easily find the integrating factor or as a complete differential. For example, if I say x dy plus y dx, is it not your d of xy? If I say y dx minus x dy divided by y square, so is it not your d of x by y? If you are given y dx minus x dy divided by x square plus y square, is it not your d of tan inverse y by x? Okay, so a little understanding will make you aware of finding the integrating factor by inspection. Some more examples I am writing. Actually it is d of x by y. Likewise, if it is in line with this, if it is x dy minus y dx by x square, it is d of y by x. It is x by y. Accordingly, it is for tan inverse of y by x. It is for log y by x. It is for this. Okay. Now let us solve one example by this inspection technique. You are asked to solve this. You see, now from this we have a standard way, x dy minus y dx. Okay, you see 5. So here it is d of y by x. One more thing, what is the derivative of this? Okay, the derivative of this is here 3x square e to the power x cube. So if we make it 3x square, so again this needs a division by x square. Okay, so now you multiply. So this implies here x dy minus y dx by x square plus 3x fourth e to the power x cube by x square dx is equal to 0. Now this becomes here what? It d of here y by x plus d of e to the power x cube, is not it? So now this 1 by x square. So therefore 1 by x square is an integrating factor of equation 1. Let it be my equation 1. Okay. Now you solve it. This is my 2. So on integrating 2 follows, it is y by x plus e to the power x cube is equal to 0, right? Is equal to some constant. So this is my answer. So once we bring it to d of something means it is exact. No need to check the exact condition then. Now these inspections may not strike into your mind. So let us see some rules to get the integrating factor. Now coming to method 2. Usually a differential equation is given of this form. We first check it exact. Del m by del y is del n by del x. If not exact, then we find this difference. Del m by del y minus del n by del x. And we divide n. We see whether the division by n is easy or the division by m is easy. If the division by n brings the function as fx, only a function of x, there is no y, then the integrating factor of this equation here is e to the power integral fx dx is the integrating factor. Okay, so this is the integrating factor. Now you see on division of m, if this is a function of y alone, right, there is no x, then the integrating factor is e to the power minus integral of fy dy. Okay, you note that there is a minus sign here, right? There is a minus sign here, right? This sign is a minus sign, but there is no minus sign here. Okay, so you mark it. So this is the integrating factor. So let us use this idea. Actually these two things are most important, as many problems can be solved by these two methods. Okay, so let us solve some examples. Now you are asked to solve two examples, example 1 and example 2. coming to the solution of 1. What is your m here? Is it not your m? And is it not your n? Because it is dx and it is dy. So in 1, what is my m? M is x square plus y square plus 2x, and my n is 2y. So what is my del m by del y? Is 2y only, and here del n by del x is 0. So clearly del m by del y is not equal to del n by del x. You see, this is not equal to this. Therefore 1 is not exact. Let it be my equation 1. Let it be my equation 2. Okay. So therefore, however, but del m by del y minus del n by del x, you see, if you subtract it, it is 2y. Now you see, the division by m will give a better answer, or the division by n will give a better answer. So of course the division by n will give a better answer. By n is 2y. So looking into this, we decide whether we divide m or we divide n. Okay, so this is 1. So 1, you see, division by n needs a function of x, right? Needs a function of x. So it will be treated as a function of x, right? So is a function of x only, right? So you say fx. So therefore the integrating factor is equal to e to the power integral 1 dx. Okay, so this is e to the power x only. So this integrating factor is e to the power x. Now multiplying e to the power x to both sides of 1. Now multiplying integrating factor e to the power x to both sides of 1. Both sides of 1. It becomes an exact differential equation. Exact differential equation. That means, that is, you just multiply it, e to the power x into x square plus y square plus 2x, that is e to the power x into x square plus y square plus 2x dx plus e to the power x into 2y dy is equal to 0 is exact. So here no need to check it. Okay, so now if you recall our previous lecture on exactness, just previous lecture, then we know the technique to solve the exact differential equation. Okay, then what is its solution? Is, since it is exact one, thus the general solution is here integral. Now this is my modified m. Okay, now this is my modified n. So I will take it this m and this n. Integral m dx, treating y as a constant. Okay, plus here integral ny dy, term not containing x, is my constant. Okay, so now I integrate it, treating y as a constant. So you see, this implies your integration of x square e to the power x dx plus here y square is constant, e to the power x dx plus 2x e to the power x dx plus, you see here there is no term free from x, so I write it 0 dy. Okay, so this ny is my 0, is my constant c1. So now I just integrate, apply by parts here. So it is x square e to the power x minus 2x e to the power x plus 2. I apply the by parts. Okay, plus here y square e to the power x integrated is e to the power x plus 2y. I apply by parts here, x e to the power x minus e to the power x. Okay, once the by part is applied, 2y by parts will be needed here, and this is equal to my, since there is a constant in left hand side, so I write this constant is my c. Okay, so this implies, taking e to the power x common throughout, this e to the power x is still there. Okay, so now taking e to the power x common throughout, it is x square minus 2x plus 2 plus y square plus 2x minus 2 is equal to here constant. So now here minus 2x minus 2 cancelled. So this implies e to the power x into x square plus y square is equal to c. So this is my answer. Okay, so this is my answer. Now coming to the second example. Now coming to the example 2. Okay, coming to your example 2, I rewrite it here. Consider this, the given differential equation is considered. Let it be my here equation star. Okay, so now this is my m, since this is dx, this is my m, this is dy, so this is my n. Okay, so what is my del m by del y? This is derivative of y fourth is 4 y cube, so 12 x square y cube plus 2x, and what is my del n by del x? It is my 6x square y cube minus 2x, so which is not equal, right? However, clearly del m by del y, so one line we may write it clear thus as del m by del y, as del m by del y is not equal to del n by del x, so equation star is not exact. Okay, is not exact. However del m by del y minus del n by del x is equal to how much? So now if I subtract it, it is 6x square y cube plus 4x. So you compare it with this, there is a mismatch in sign, you compare it with this, it is a matching with this. Okay, so we divide m here, if we divide m here, and this will be, m will be my 2 times 6x square y cube plus 2x. You see here one y is there. Okay, this one y will be there into one y. Okay, so now this and this cancelled, right? Just there is a error in the denominator, so I write the denominator as like this, and I write the denominator as simply it is 3 x square y cube I write plus 2x I multiply y here, take common. So now in the numerator, if I take 2 common here, it is 3x square y cube plus 2x divided by y times 3x square y cube plus 2x. Now this and this cancel here, it is here 2 by y. You see, is it not a function of y alone? So the principle says your method 2, if you divide by m, you should ensure that it is a function of y. If you divide by n, it should be a function of x. So now we are dividing by m, so it is a function of y, right? So what is the integrating factor? So therefore integrating factor is equal to e to the power minus of fy dy. Okay, minus of fy dy. So you see there is a negative sign here, but in previous case there is no negative sign. It is e to the power minus of 2 by y dy. Okay, so this will be e to the power minus of 2 ln y. So this is equal to e to the power ln 1 by y square. E and ln are inverse of each other, so this is 1 by y square. So this 1 by y square is an integrating factor. I multiply this with star. Now multiplying the integrating factor to star, we get the corresponding exact equation. Now you see, if I multiply this to both sides, okay, now y square is divided, so this is 3x square y square. So now this will be the equation, and it is my, already it is exact. Okay, already it is declared that it is exact, no need to check it. Okay, no need to check it. So thus its general solution is, okay, integral of this 3x square y square plus 2x into 1 by y dx. We treat y is equal to constant here, plus here there is no term free from here x, so it is 0 dy is some constant c1. Okay, now we are treating y square constant here. So this is 3y square into x cube by 3 plus 1 by y is constant here. It is 2x square by 2. Okay, plus there is some constant here, you say is c1. Okay, now you adjust them, this 2 and 2 cancel, 3 and 3 cancel. So this implies here x cube y square plus here x square by y. Now this constant c1 minus c2 is my c. Okay, so this is my answer. Now coming to the fourth methodology. Now coming to two more methods. So this is the usual form as we know. Now once this is a homogeneous one, by inspection we can see once it is a homogeneous one, then the integrating factor will be 1 by m into x plus n into y, right, provided this denominator is not equal to 0. We know the usual technique, putting y is equal to vx we can solve it, but it is a lengthy approach. However, if this denominator here mx plus ny consists of a single term, then this integrating factor technique will be an easier approach. Okay, now coming to another method. If this mxy dx plus nxy dy takes the form fxy into y dx plus gxy into x dy. Okay, means this is again a function of xy. It can be again a mxy, it can be again a nxy. However, y may be an explicit here, x is explicit here. If it's seen like this, okay, then your integrating factor is equal to 1 by mx, m into x minus n into y. Here it is mx plus ny, you see, and provided the denominator is not equal to 0, provided mx minus n into y is not equal to 0. So let us see some example to solve the problem by these two methods. Now coming to the solution of 3 here. Solution 3, you consider this. You see here this is my m, here this is my n, right? It is not exact, but you see this power is 2 plus 1 3, this is 1 plus 2 3, so this is 3 and this is 3, so it is homogeneous, right? Let it be my equation 1. Solution here. Equation 1 is not exact. You can check it. Not exact. You can check. Del m by del y is not equal to del n by del x. But it is homogeneous. So you can proceed by homogeneous technique. But once we see, but it is homogeneous. Thus, we see mx plus ny, mxy x times this plus y times nxy we see. Okay, we add it. If it is a single term, so you just add it. So now if you multiply x with this and y with this and you add it, then here this and this cancelled. So this is here and it is subtracted, x square y square. You see it is a single term. So this integrating factor approach is a easier approach. So therefore integrating factor is equal to here 1 by mx plus ny is here 1 by x square y square. Okay, 1 by x square y square. Now you multiply this to both sides of 1. Now multiplying 1 by x square y square to both sides of 1, we have. So if you multiply this, we get this, and if you just simplify it, it is x square cancelled, 1 by y minus 2 by x dx, and it is minus of x by y square minus 3 by y dy is equal to 0, which is exact. No need to check, which is exact. Okay, which is exact. So let it be my equation star. Thus the general solution of star, general solution of star, or we may say the original one, the general solution of 1, or we may write star, is given by the integration of this treating y as a constant, 1 by y integral of dx minus 2 integral of dx by x, and it is minus plus here. It is not free from x, but it is free from x. It is integral of 3 into 1 by y dy is equal to some c1. So once you integrate it, it is x by y minus 2y, this is log x, plus it is 3 ln y is equal to here c. Okay, we may leave it here or we can simplify it. Now this is my answer. Coming to the second example. So now you are given this example 4. So now this is my m. Okay, this entire thing is my m. You first take m, and this entire thing is, first you check the exactness. Okay, but you see here del m by del y, okay, is not equal to del n by del x. First you see whether it is exact or not. Thus star is not exact. However, it is of the form, you see y is multiplied here explicitly, x is multiplied. It is fxy into y dx plus gxy into x dy, okay, is equal to 0. So the chances is there. Under method 5, that 1 by mx minus ny. So we find 1 by mx minus ny, and mx minus ny is with mx minus ny is equal to, you just multiply it. So this mx minus ny, it will be this and this cancelled, and xy cancelled. It is 2x square y square. So therefore my integrating factor here is 1 by mx minus ny is 1 by 2x square y square. So this is my integrating factor. Now I multiply integrating factor to both sides of star. So now you multiply the integrating factor, it will be like this, and if you further simplify it, just 2 will be taken out, 2 is multiplied throughout. It is my y, and y is here, so it is y plus 1 by x plus 1 by x square y, okay, into dx plus here x minus 1 by y plus 1 by xy square dy is equal to 0, which is exact. Okay, which is exact. Okay, now once it is exact, the solution of double star is nothing but the solution of star. Thus the general solution of the given differential equation is, thus the general solution of the given differential equation, right? It is for the original equation. Given differential equation is, okay, now this is my m, this is my n, right? This is my n and this is my m. Integral of m dx y equal to constant plus integral of ny dy is equal to c1. Okay, so this is my general solution. So this implies I have integration of y plus 1 by x plus 1 by x square y dx y equal to constant, and here you see this is not free from x, this is not free from x, however this is free from x, okay, plus integral of minus of 1 by y dy is equal to some c1. Now if I integrate it, it will be my xy plus it is my log x, and plus it will be 1 by y is constant, it is minus 1 by x, so it is minus 1 by xy, and it is minus ln y, and some constant is here, c2 is equal to some c1. Now so this implies here xy minus 1 by xy, and this collected together, plus ln x by y is equal to some c. So this is my answer. Okay, this is my answer. Now coming to the summary of the discussion, you are given a differential equation mxy dx plus nxy dy equal to 0. You first see it for the variable separation. Okay, this should be first it is given to you. First you see for variable separation. If it is easy to see variable separation, then you proceed. Otherwise you check for exactness. Once exact, then fine. Otherwise see the integrating factor or homogeneous, and accordingly you proceed. Okay, so with this, some assignment problems are there. 5 assignment problems are given to you, and you should solve it, and you should refer any standard book to solve for more problems for your practice and awareness. With this, my appeal to all of you is that if you feel that this lecture is useful and interesting for you, please like and subscribe to my channel. So whenever this new lecture will be uploaded, it will come to your screen. So thank you all. Have a nice day.